in the electric motor system, we have just looked at the electrical system reliability. Okay, so we want to look at the mechanical system reliability. Now, remember, in the electric motor system, we looked at the input power to the electric motor. So now I want to look at the electric motor and the load that is attached to the electric motor. Okay, so like we said earlier, the load could either be pump, fans, compressors, and what have you. And between the electric motor and the load, we have what is called the coupling. That is the means with which the rotating mechanical energy is transferred to the load. Are we getting it? So we are going to look at the electric motor now and the load. Okay, because as we saw earlier, the electric motor also have some mechanical components that can affect the operations or the reliability of the electric motor and thus the electric motor system. So components like the bearing, okay, which actually help to ease the rotation of the rotor within the stator of the electric motor. So that component have a way of affecting the operations of the electric motor if it is bad. Then the rotor itself, remember, it is expected that it will be rotating constantly. We also see some of the things that can affect it, like unbalance, that will affect the operations of the electric motor mechanically and thus the entire electric motor system. So one of the most notable means of looking at the mechanical integrity of the electric motor system is vibration measurement and analysis. Okay, so we know that as the electric motor is working, its component parts, they usually vibrate. Now when we say vibration, we mean the to and fro movement of this component about a main position. That is the molecules of this component about a main position. Okay, so this vibration, we have what is called the normal vibration when the equipment is operating normally, and then we have what is called the abnormal vibration that is introduced by fault condition, that is caused by fault condition. Okay, so we have simple instruments like the handheld vibration meter that will be able to give us the overall vibration level of the electric motor and the pump. So if we take the vibration readings, okay, of the electric motor at the bearing housings or around the bearing housing, as we'll see later in three positions or orientation around the housings. Okay, so we'll be able to get the overall vibration reading with the vibration meter. So when we are trending this overall vibration reading, as the vibration of the equipment, the total vibration is changing, as it's increasing, we'll see it. And what is actually guiding this is the bathtub curve. Okay, so as the that parameter, that is the vibration level that we are looking at, as it's entering the PF area, that is point of potential failure and eventual failure area. Okay, you will see that we will see it with the handheld vibration meter that will give us the overall vibration level. So when it's entering that area, as the vibration is increasing, we can now use the vibration analyzer, okay, that will help us to analyze and determine the cause of that increased vibration. So this is the analyzer that, as you can see, on the left of your screen, and this is the vibration meter. So these are instruments, okay, that we can use to monitor the vibration levels of the mechanical systems of our electric motor. So we are going to look at each of these instruments and how we could use them in the field, okay, on the electric motor. Now, like we said earlier, we have three orientations or positions that we can measure the vibration of the electric motor on each of the bearing housing, okay, or points. So now if you look at the motor itself, on this housing we can, since we have two bearings, okay, one on the drive end and the other at the non-drive end. So the one at the drive end is called the inboard bearing. The one at the drive end is called the inboard bearing, and the one at the non-drive end is called the outboard bearing. So the three positions are the vertical position, okay, that is the position that is at right angle, vertical right angle to the bearing on the housing. Then we have the horizontal position, as you can see on your screen here, okay. So if you look at this diagram, this point where you have the pointer is the vertical position, and here, okay, let's say here, because this is the cover, the fan cover, okay, so we will not get much information here. Let's say here, okay, that's the vertical position, and then here is the horizontal position, okay. So the position that is axial to the shaft, that is in the same axis with the shaft, is called the axial or axial direction. So we can look for any, like any part of the motor that we can take such reading axially, okay, and that will give us a reflection of what is happening around the bearing. So on the motor we have basically three measurement position and three measurement on the outboard and three measurement position in the inboard. That is what is stated here: motor outboard vertical, motor outboard horizontal, motor outboard axial or axial, okay. Then on the inboard, definitely, you know, we can only take the vibration reading when the equipment is working, okay. So for safety purpose, it may not be feasible to take the axial reading around the inboard end because of the shaft that is rotating and it may be covered, but we can take the horizontal and vertical vibration reading. Then on the pump end, the same thing too. We have the inboard, that is the part that is attached to the coupling, and then we have the outboard, okay, that is the part outside on the other part, on the other side of the shaft. Are we getting it? So those are the measurement points, okay, that we can take our vibration reading, which means that each time we go out to carry out vibration on a system like this, we have roughly 5 points here, 5 points here, that is 10, but ideally it is supposed to be 12, I mean to say 6 on each. So if it is possible, of course, because there are information that the axial vibration will give us. Are we getting it? So if it is possible, we should take the axial vibration reading also, okay. So all of these vibration information that we get, what information, or the vibration reading that we get, what information about the health of the electric motor, about the reliability, or that is about the integrity of the electric motor, it will give to us, okay. It will make us know, so that we'll be able to improve the reliability of the electric motor if need be. So as you go to measure like this one now, you can see that he is taking on the vertical position on this electric motor. Okay, so if it is the handheld vibration analyzer you are using, it will give the handheld vibration meter that you are using. It will give you the overall vibration level. So the only thing that can do for you, as we stated earlier, is just to help you to know when the vibration is increasing. So once it's increasing, you know something is developing within the electric motor. Are we getting it? But the drawback is that before it will show up in that increase, it may have gone far into the PF region of your bathtub curve, and it may not be recoverable again. That is, you may have little or nothing to do, or you may not be able to bring the situation back to what is close or what is normal or close to normal. Are we getting it? But if you have the vibration analyzer as it is developing in the incipient stage, okay, you may see it. Now look at this analyzer as is used in the field. So you see the waveform on the analyzer, okay, looks like something on the right. This is the waveform. So to the ordinary eye, this waveform does not make a lot of sense. It's just like the voltage and current waveform that we saw with the power quality analyzer the other time. So here we have the effect of other forcing function, okay, that is other harmonics that are superimposed with the vibration waveform of interest. Okay, that is what is causing all of this distortion. But even at this, if you look at it critically, you will see a pattern. Are you getting it? And this pattern, this increased vibration, if you also look critically, you will see that they are occurring at regular interval. That will give you a sense as to the fact that something is happening at these intervals. Okay, it could be in pattern, especially if you look at these intervals coincide with one-time RPM. Are we getting it? So that is the beauty. But what is actually causing this vibration? Like we did in the voltage waveform, we can do fast Fourier transformation on this vibration waveform. Okay, and that will be able to separate each of the vibration waveform that we have, okay, into their respective frequencies. And the beauty is that various fault conditions in the electric motor, on the electric motor and even on the pump, okay, they appear at different frequencies, as you can see, as we will see later. Okay, so if you look at the analyzer, this is the spectrum that is underneath the waveform. Okay, so with this, you'll be able to know what is actually causing that increase in vibration, or what is causing this impact that you are seeing on this waveform. Okay, so with the experience and the rest, you'll be able to ascertain the causes. One important thing that most vibration analysts fail to do, and asset managers they fail to do also, is that they feel that when we have fault condition, you just bring your analyzer. The analyzer will be able to pinpoint what is actually causing the problem. It may be able to give you, okay, but you have a better understanding of what is happening if you have been taking your vibration reading, carrying out vibration analysis regularly before, so that as you take, when the equipment is good, you try to analyze the waveform, the spectrum, to identify each of the forcing functions, okay, in that electric motor on the spectrum. What I mean is this. Let's take the electric motor for example now, okay. We have the bearing. We know that the bearing, okay, let me start from the rotor. We have the rotor, okay. That rotor, since it is rotating, it contributes its own level of vibration into the overall vibration of the electric motor. Are we getting it? And on each end of the shaft of the rotor, we have bearings. And if we are looking at ball bearings, you see that these balls, as they are rotating within the bearing race, either both the inner and the outer bearing race, you will see that it is also introducing some level of vibration. Okay, so if we are able to identify the frequencies at which the vibration that is caused by the rotor, the one that is caused by the bearing, okay, then on the pump side, the one that is caused by the bearing at both ends, then the one that is caused by the impeller itself, which will be the number of vanes that we have on the impeller times the speed of rotation. Okay, that is the fundamental frequency. So if we have 8 blades, okay, so the contribution of the impeller into the overall vibration will be seen at 8 times the speed or frequency, fundamental frequency of operations of that particular pump or electric motor, if it is not attached to a gearbox. Are we getting it? If you are able to identify all of these forcing functions, okay, when the equipment is working fine, when changes are happening, you'll be seeing them on each of the analysis that you carry out on each of the vibration measurement that you go out to the field to do. Okay, so as situations are developing negatively around the bearing, around the rotor, around the impeller, are we getting it? You'll be seeing them. Okay, and then if it goes beyond the level that you feel could be tolerated, then you can flag off the alarm, so that what needed to be done to bring back the condition to normal should be done, so that the vibration levels will reduce again. Okay, so